the AP Calc 2023 questions are out. AB and BC. So I'm probably going to do both of them. I bet a lot of them are overlapping, though. But we'll still look at both of them. So I do want to add a page, I think, and try to do these clean. Put it on some graph paper. Okay. So what do we have here? This problem just looks so familiar. I saw this problem and I was like, I literally thought I downloaded the wrong one at first. Because it looks so familiar. But no, it says 2023 right at the top. That's this year. That's what it says on the bottom right of the screen. All right. A customer at a gas station is pumping gasoline into a tank. The rate of flow of gasoline is modeled by a differentiable function where f of t is measured in gallons per second and t is measured in seconds since pumping began. Selected values of f of t are given in the table. Using correct units, interpret the meaning of the integral from 60 to 135 of the function in the context of the problem. Use right Riemann sum to approximate the value. Okay, so when you take the integral of a rate, you get a value. So that will be the amount. Hang on, I literally just said I wanted to do this down here. 1a. 1a. The volume of gasoline in gallons pumped into the tank between 60 minutes and 135 minutes from beginning pumping into the tank between 60 seconds after they started pumping and 135 seconds after they started pumping. I should have copy and pasted that, but that's okay. So let's reread it. The volume of gasoline in gallons pumped into the tank between 60 seconds after they started pumping and 135 seconds after they started pumping. Yep. We use units both ways. Beautiful. Now we calculate it using the right Riemann sum. So just a quick, I like to do a little sketch out just to show what we're going to do. These are like the rectangles that we have. So we're doing it from 60 to 135. And look at how like the first rectangle uses the second value for the height. And then we just think about them as rectangles. So I am going to do it up here and then I'll copy and paste it down. It's going to be, so the first rectangle is 60 to 90. So 30 times the height of that rectangle, which is 0.15. And then plus 90 to 120. So that's another 30 times the height of that rectangle, which is 0.1. And then the last one has a different width of the rectangle. See there, 120 to 135, that's only 15 times the height of that rectangle, which is 0.05. And this is a calculator problem? Yes. So 30 times 0.15 plus 30 times 0.1 plus 15 times 0.05 is 8.25. Then you think, does that make sense? When you pump gas into your car, do you pump it about 8 gallons a minute? Probably. It's unfair to the freshmen taking AP Calc or the sophomores taking AP Calc, maybe. Okay, I'm actually going to recopy that. So to calculate it, we're going to go 30 times 0.15 plus 30 times 0.1. That's why it looks so bad, because I was writing too big. Plus 15 times 0.05 equals 8.25. I just got electrocuted by my wire. That's what that was. Okay. 8.25 gallons. Very good. Okay. That's all they wanted, right? Approximate that value. Yes. Okay. B. Must there exist a value of C, for C is in between 60 and 120, such that f prime of C equals 0? Ooh, so they're talking about mean value theorem. Right? That's what that is? Yeah. So we're going to say B, because f of t... Wait, they gave us f prime, didn't they? Gallons per second? Yeah. Well, since it's differentiable... Oh, wait, so it's not going to be mean value theorem, because what they're giving us is f prime. Wait, no. F is in gallons per second. Oh, interesting. So they're already giving us a gallons per second. It's like they're already giving us a derivative. Okay. Well, that's why it wasn't f prime in part A. That's why it was just f, because f already was the derivative. It already was a rate. Okay. Oh, well, so f prime. So here they're still talking about f prime. Okay. So the derivative of the derivative, but it's still f prime. So this is mean value theorem, because it's the prime of the function we have. So we say because, and f of t, that's the differentiable. Well, that's differentiable, because f of t is differentiable, and therefore continuous. Rolle's theorem is a specific case, right? With just this, you can say that mean value theorem applies. We're not saying it equals 0. In this case, we are saying it equals 0. But just in general, mean value theorem applies if it's continuous and differentiable. And so that allows us to say, that allows us to find the average rate of change. So we'll do, and it's between 120 and 60. That's what, we can do that, right? I'm less confident now that this is mean value theorem. But no. Yeah, it is. It is. I'm still getting confused with the intermediate value theorem, but that has to do with not derivatives. This one has to do with derivatives. So what is 120? Is this not the way to go? Maybe this isn't the way to go. Well, let's go ahead and calculate this. What is f of 120 is 0.1. Oh, yeah. 0.1. Okay, yeah, no, it works out nice. Yes. Because f of 20 is 0.1. F of 60 is 0.1. And then this is just 60. So that's 0 over 60. So that's 0. So we say, like, the average rate of change from t equals 60 to t equals 120 is 0. Therefore, there is at least one value C. I'll go ahead and use inequality. such that 60 is less than or equal to C is less than or equal to 120, where f prime of C equals 0. I mean, that's fair. Did I make that harder than it needed to be? Very possibly. Because what's the reality of it? The reality of it is like, it goes up to 0.15, goes back down to 0.1. So therefore, it would have had to turn around at some point. But that's basically what I said. That is what I said, just like in mathematical speak. We didn't have to find that C. It just said, does it have to exist? So we're not going to waste time finding it. Actually, we can't find it because it's just a table. Okay, part C. The rate of flow of gasoline in gallons per second can also be modeled by that. Using this model, find the average rate of change over the time interval 0 to 150. Find the average rate of flow of gasoline. Oh, average rate of flow. So just average rate of flow from 0 to 150. Just think about, we're going to get the total amount of flow. And then we're going to divide by 150. Right? And how do you get the total amount of flow? That's the same thing we did in part A. It's just here we're going to do it in the calculator. So we're going to do, I don't know, we don't actually have to show hardly any calculations at all to be thorough. We just have to say we're going to do the integral from 0 to 150 of g of x dx. And then we're going to divide by 150. Frankly, that's all the calculations you have. So how are we going to do this quickly? That was the real question on a numworks. So we're going to we're going to come over to the grapher and we're going to say f of x, and we're going to type in the equation. So it's going to be x over 500 times the cosine of x over 120 squared. And then we don't need to plot it. We need to come back to calculations now, and we need to do calculus integral from 0 to 150 of alpha g, except I called it f. Oh my gosh. Alpha f of x divided by 150. Boom. 0.096 gallons per second. So let's do this. Let's look at our answer for part A and see not necessarily how similar it is, but see if it should be like we should be able to make the same sense out of it the same way we did when we did part A. 10. I mean, that's more. That's like a lot more. But I was also like, we didn't do a good, decent estimation. So when we're talking gallons per second, yeah, I suppose that makes sense. About 0.1 gallons per second. Tenth of a gallon per second. 10 gallons a second. 10 seconds a gallon. That makes sense. Okay. So that's equal to 0.09600, right? That's plenty of decimal spaces. I'm going to leave it there and not mess it up. And that's everything, right? Using this model, find the average rate of flow over the time 0 to 50. Show the setup for your calculations. Well, yeah, that's the setup for my calculations. Okay. D. Using the model G, defined in part C, find the value of G prime of 140. And that's what's so beautiful, well, yeah, about typing it in like that, because now what we're going to do is we're going to come here, is it can't just, in general, find the derivative, but it can do it for specific values. So what was it, 140? Boom. Negative, down here, D is negative 0.00491. And that's the derivative of G prime. So that's in like a per second type of thing, right? Because F, or also G, is in gallons per second. So when we take the derivative of that, we get the acceleration. So it's going to be in gallons per second squared. Per second. I'm going to write per second squared. So that means it's slowing down. So this means 140 seconds after beginning pumping, the rate the gasoline was going into the tank was slowing down by, so not negative because I said slowing down, 0.00491 gallons per second per, that was gross, per second. Yeah, that's interpreting. Okay. That's it. We move on. What is our time? We're supposed to have 30 minutes. It means we have 12 minutes left. Oh, no. All right. Steven's swimming. Oh, it's swimming. Oh, but it's in a 50-meter pool. Along a straight path in a 50-meter pool for 90 seconds. How did he do that? It just took him that long? Steven's velocity is modeled by the velocity, yada yada, where t is measured in seconds and v of t is measured in meters per second. Find all the times in 0 to 9 where Steven changes directions. Find a reason for your answer. Love it. So let's add a new page. And let's say A is, we want to know, well, that's his velocity. His velocity is modeled by that. So we just want to know where his velocity, where v of t is equal to 0 and where v of t is undefined. Now, undefined, we could probably do that for ourselves, right? Where is v of t going to be undefined? Because it's just the function being undefined. And that's never. There's no value of t that's going to make that undefined. So we're really just looking at where it's equal to 0. So then we just bring out handy dandy. Yeah. And we'll go to solver. Are we looking at an interval? 0 to 90. Yeah. Okay, so we'll go to solver, or equations nowadays. and type in this bad boy. So 2.38 times e to the negative 0.02, call it x, times the sine of pi x over 56. Boom. Equals 0. That's what we wanted. Solve equation. Minimum 0. Maximum 90. Wabam. Solve equation. 0 and 56. That is a lot less than I thought it would be. Well, 0 is not actually included in the interval, so we don't actually include that. We just say t equals 56. What a number, 56. How did that happen? Oh, because pi over 56. Got it. Okay. So, but then we need to look at, so that's like our critical value in a way. So then we should look at like what is v of 55 and what is v of 57. Ooh, I don't know if I can do that from here. I can do this. I can call that x. I could come in here and call that 57. And come here and call that times 57. And then solve for x. How is there two values for x? Oh, because I left an x here. Love it. Negative. V of t is less than 0. But then when we come in and change this to, ooh, that was 57 was less than 0. So when we change that to 55, it is greater than 0. Therefore, he changes directions. Oh, did he go there and back? I thought they were to make it sound like he went one way. Therefore, he changes directions at t equals 56. It does say swim back and forth. Okay. Yeah, there we go. We're done. B. Find Stephen's acceleration at time equals 60. Show the setup for your calculation and indicate units of measure. Is he speeding up or slowing down at time equals 60? Okay, time equals 60. So that means we're going to find v prime of 60. That's the setup for the calculation. I don't know how they could possibly want us to be any more specific. However, this is a problem that I'm just going to retype this in, honestly. I'm just going to go to... Well, I might have to use it again. So let's type it in Grapher. I probably should have just done this the first time. So what was the equation? It was 2.38 e to the negative 0.02 x times the sine of pi divided by 56 x. Okay, so now we have f of x. Now we come here and we do this exact thing except for at 60. Right? And let me do this just to make sure that that's a different answer. Now it is. Okay. So yes, this is approximately negative 0.00289. What are the units? I mean, it's acceleration. So it's meters per second squared. Lots of acceleration. Meters per second squared. Okay. Show the setup for your calculation. Indicate units of measure. Is Steven speeding up or slowing down? So speeding up or slowing down is like if the velocity is the same sign as the acceleration. So what we need to do then is we need to find v of 60. Or on here, f of 60 is negative. And right, we could have known that because he turned around. I'm going to say that v of 60 is less than 0. So, because his velocity and acceleration are the same sign, he is speeding up. Okay. Find the distance. How much time do we have? 3 minutes. Find the distance between Steven's position at time equals 20 seconds and his position at time equals 80 seconds. The distance between the positions. That's displacement, so we don't have to do any absolute value. So C is just the integral of v of t dt from 20 to 80. So we already have that out. So let's just go to calc. Let's go to integral 20 80 of f of x is approximately 23.38 meters. That's it, right? Yes. D. Find the total distance he swims over that time interval. From 0 to 90. Okay. That was not what I wanted. So from 0 to 90. So he turns around at 56. We already know that. So we've showed that he's going backwards already at the other ones. So we know we need to go from 0 to 56. V of t dt. But then since this is going to be a negative, we need to subtract from 56 to 90 v of t dt. And that's really it. So whether I have time to type it in, especially as I'm already doing it so slow, I'm going to come up to here. We're going to go from 0 to 56 minus the integral from 56 to 90 f of x. And again, that's because he changes directions at 56. 62.164. And that's all we needed here, right? Yeah. I feel like by saying show the setup for your calculations, that means they didn't even want you to get the numbers. But We finished it in 30 minutes, or at least the recording is 30 minutes, which is all I know. Are you a math major? Yeah, I majored in math a few years ago. So that was the first two questions. Let's take a quick little break and let's check our answers. Also, I don't know why I'm writing in black. That's awful. So here's how we're going to check the answers. We have to check our answers by getting them from here. So let's come back out here. Where are they? Right here. Shoot. So we were all good. The only thing that was slightly wrong was this answer right here. Look at how, you remember how we did that extra value to test that it was doing a new function? But then when I wrote down the answer, I wrote down the value of the new function instead of the correct value that it was supposed to be. So I made that correction. Other than that, we're good to go. So let's see what we're looking at. You know what? I'm going to do one more thing. I'm going to add a timer. A bottle of milk was taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of the milk at time m of t is measured in degrees Celsius, and t is the number of minutes since it was placed in the pan. What is this situation? M satisfies the differential equation d of m1 for the time t equals 0. The temperature of the milk is 5 degrees Celsius. It can be shown that m is less than 40. M of t is less than 40 for all values of t. A slope field for the differential equation is shown. Sketch the solution curve through the point 0, 5. Okay, easy enough. We'll just do that right here. So, what are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes. So, we're looking at 5. Wait, is that our starting point right there? 0, 5? Oh, okay. So the idea is you just gotta always be parallel to these lines. Let's change colors. So you can like cross them like that. It's just that like while you're going over them, it's like they always have to be parallel. Let me do a little partial erase here. I feel like it's good up to there, but then yeah, it was probably good before, to be honest. Yeah. Okay. Arrow. Beautiful. Use the tangent to the graph of m at t equals 0 to approximate m of 2, the temperature of the milk at time t equals 2. Okay. Use a tangent to the line. All right. So let's add our new page. And let's go 3a, 3b. We're going to copy down our equation like this. And then we want to look at 0 and 2. So we'll say if m equals 0, then it's 40 over 4. Then dm dt equals 10. So what we do then is we write the equation of the tangent line, which is 10 t Or 10x. No, m of t. Yeah. Oh yeah, dy dx, so it's t. So it's 10t plus 5 equals m. And then we want to find it at 2. So then we say equals m of t. So then we'd say that m of 2 is 25. Do we need units? Temperature of the milk at time equals 2. 25 degrees. Love it. Okay. So that's just a tangent line approximation. So that's what in the brief picture we saw of the other guy, he did something like that, and it was like they calculated that point there. We just calculated that point there. Okay, write an expression for the second derivative in terms of m. Use the second derivative to determine whether the approximation is an overestimate or underestimate. We've done all of this stuff before. Okay, so C, we need to find the second derivative. So we're going to have to use probably differentials all the way, right? So we'll take the derivative, and we'll get our second derivative here. And so then we take the derivative, so that's 1/4 negative, 1/4 times negative, so negative 1/4 times the derivative of m, dm dt. And then what is dm dt? Dm dt is this thing up here. So it's negative 1/4 times 1/4 times 40 minus m. I kind of feel like I'm just making all that up. And then let's just distribute the negative. So let's make it m minus 40 over 16. That seems pretty good though, honestly. No, that seems pretty good. Okay. So yeah, I guess. Or is it not? Is it just negative 1/4? Did I do that? Did I try way too hard with that? Because if that was an x, I would just take the derivative again. Oh yeah, because it's m, because in dy dx, yeah, because it's m, you have to do that. That's why it's not, because that's not our x variable. If that was just a t, then we would, because it'd be dt dt. But since that's our y variable, like our m is like our y variable here, you do have to do it like dm dt, because we're not taking the derivative with respect to m, we're taking the derivative with respect to t. So you do need the extra dm dt. So you do need to do that. Love it. Got it. Okay. So then we need to find, we already know this. We already know that it should be negative at time equals 2. So when it's a function of m, how does that really work? So we have to say that it's negative from 0 to 40. So we have to say that d squared m over dt squared is less than 0 if m is less than 40. And then we say that therefore it's an underestimate. I think we can just say therefore it's an underestimate. Because I think about like the concavity, like it's concaving down. We can also just so easily see that. Therefore it is an underestimate. Okay. D. Use separation of variables to find an expression m of t. Find the particular solution. So we need to start with this. Let's change colors again. We've got to start with this and separate our variables. So we've got to get the m's with the dm's, and then if there were t's, we get them with the dt's. There's just not in this case. But so that means we have to divide. So we can leave the 1/4. So we'll have 1/4 dt, and we'll have 1/40 minus m dm. And then we'll integrate both sides. So we'll have 1/4 t, throw the plus c there. And then this is ln, right? But it's a negative. So negative ln 40 minus m, because m is negative. So let's make sure that checks out real quick. So we take the derivative, it's 1/40 minus m. And then you'd multiply by the derivative of the inside, multiply with a negative. That would cancel the negative out. So yeah, there we go. So that's like the general solution. And then we have our particular solution. So we can find c. Because what are we using? 0, 5. So then we plug in t equals 0. So when we do 1/4 times 0, that's going to be the same as when we do that minus 5. This is plus c. So that's all just 0. So we get that c is negative ln of 35, or ln of 1/35. But negative ln of 35. Okay. Oh, because they probably want us to do like some other weird e stuff and just get like a 35. How do they want us to write the answer? Find an expression for m of t. That's right. That's right. So we actually don't want to do this yet. We want to get m by itself first in an ideal world. So that's fine. Let's move the negative just to the other side. So that just means we make that a negative. Because here's what we're going to be doing a lot with this. Is negative c is still just a c. So we're not going to change that at all. We're just going to have it be a different c value. And then we're going to get rid of the ln. So we're going to do e to the 1/4 t plus c equals 40 minus m. And now we think about the same thing. So we're going to split this up. We're going to say that this is e to the negative 1/4 t times e to the c equals 40 minus m. But e to the c, e raised to a constant, is still just a constant, right? So this is really just c times that. And then, so now to get m by itself, we'll just multiply both sides by a negative. And then, but again, we're going to multiply both sides by a negative. So we multiply c by a negative, that's still just c. So we're just going to have c e to the negative 1/4 t equals m minus 40. So then we can add 40 to both sides. And I don't think there's anything we can do with that c there. With that 40. I think we'll just have to leave it like that. And then now we get that equals m. And so the deal is now we'll get our c value and it will like just be 35 or something like that. So c, so now we plug in 0. So c times e to the 0 plus 40 equals 5. C, z to the 0 is 1. So c is negative 35. So the actual equation is, let's come back up here for it, negative 35 e to the negative 1/4 t plus 40 equals m. That is the exact equation for this. Beautiful. There we go. Okay. Let's check our answers now. No, let's not check our answers now since we're timing ourselves. Let's go to the next question. 4 at a page What do we have? We have an hour, right? We have 20 minutes per. Oh, it's 4, so we have 15 per. Shoot. Okay. Well, not shoot. We're looking good still. 4. The function of f is defined on the closed interval -2 to 8 and satisfies f of 2 equals 1. They give us f prime. The graph of f prime is shown. Consists of 2 line segments and a semi. Does f of x have a relative minimum, a relative maximum, or neither at x equals 6? Give a reason for your answer. X equals 6. Okay. So here's going to be the reason for our answer. Well, first off, we're going to copy this graph down here so we can look at it easier. Forget it, you don't have to tap after that. I didn't mean to paste. Okay. Copy. Paste. Close. A. So we want to know about 6. So I think it's neither, right? So we say like f prime of 5.9 is greater than 0. F prime of 6.1 is greater than 0. Therefore, there's a point of inflection. Or I'll just say, what did they ask? They just asked if there was a min or a max. Yeah. Therefore, there is no min or max. I don't know what more they'd want me to say for that. B. On what open intervals, if any, is the graph concave down? Give a reason for your answer. Okay, so when it's concave down, that's super easy enough. Concave down means that f double prime of x is less than 0, which means that the slope of the derivative is less than 0, because we have the derivative, right? So we need to look at the slope of the derivative. So absolutely, from -2 to 0. Also, from... Hang on. Wait, no, this is right? Just concave down. Yeah, we're only looking at concave down. I was thinking of like speeding up or something. We're only looking at concave down. So we only need the second derivative to be less than 0. So that's from -2 to 0, and that is from 4 to 6. Cool. C. Find the value of that limit or show that it does not exist. Justify your answer. Whoo. Okay. This actually just looks like it's math. Can't we just do some factoring? Oh no, because it's f of x on top. Okay. So it's f of 2. So that's the thing, is that we actually just know this equation. So that's how I'm going to do this. I'm just going to say we know that f of x, that part of the piecewise function is x plus 2. X minus 2. So I'll say like when 0 from x to 4, f of x equals x minus 2. So therefore what we have is 6x minus 2 minus 3x over, go ahead and factor that, x minus 2, x minus 3. So then up top, oh, that's kind of weird we got the x minus 2 there. We're just going to ignore that though. So 6x minus 12 minus 3x over x minus 2, x minus 3. So then that's 3x, that's 3. X minus 4. I don't think it exists. I don't think it exists. Because I don't think there's any way to cancel out that bottom. Or you know what they actually want me to use is L'Hopital's rule. Let's actually use L'Hopital's rule. That probably will be easier. So first off, I have to plug in, and I have to say that 6 times f of 2 minus 3 times 2. Oh, but I can't even use L'Hopital's rule. So, yeah, it definitely doesn't exist, because f of 2 is 0. Wait. F of 2 is not 0. Hold on. What is f of 2? Did they tell us what f of 2 is? F of 2 is 1. F of 2 is 1. F of 2 is 1. Okay. So that was my problem here. That's actually not true. F of x is not x minus 2. F prime of x is x minus 2. So I could do that same thing. But no, this is going to be quicker. This is going to definitely be quicker. Equal, so this is 6 minus 6, which is 0. And then the bottom, when you plug in 2, is 4 minus 10 plus 6 is 0. So we're going to use L'Hopital's rule. And then that means we need to take the derivative of the top and the derivative of the bottom. So it's going to be 6 prime of x minus 3, that's the derivative of the top, the derivative of the bottom, 2x minus 5. And we're finding the limit of the same thing. And look, now we can find the limit because we can just plug it in. So we're just trying to do 2 times f prime of 2 minus 3 over negative 1. So what is that? 3 minus 6 times f prime of 2. Now f prime of 2, that's what that is. That's 0. 6 times 0. So therefore it's 3. Therefore the answer is 3. Okay. That's all they wanted here? Okay. Find the absolute minimum of the function. So the absolute minimum means we need to see where the... Ooh. We need to see where the derivative is negative 2 is 0. But really we just need to think of where it actually is. So these are like derivatives. Right, they're derivatives. So I'm going to try to think about the integral. I want to try to think about doing the integral because what? We want the absolute minimum. So we want to know from negative 2 to a of f prime of x dx is minimized. Should I actually just use that idea? How do you minimize that? You take the derivative of it? Well, no, because then we're just f prime and then we're just checking stuff. So I just want to try to look at it. So I want to be like, here it's going forward, it's going forward, it's going forward, it's going backwards, it's going backwards, it's going backwards. It's back to where it started. And then it's going backwards, it's going backwards, it's going backwards. But then it's going forwards, it's going forwards, it's going forwards. And so it's back to where it started. But here it's going more backwards. So that's at x equals 2. I mean, it's a equals 2. Because it's moving... At time equals 0, it's where it started. At time equals 0, it is where it started. But then it moves backwards. It's not a particle though. It moves backwards until t equals 2, where I'll say it goes down. Until t equals 2, where it starts going up and continues going up. Yeah, that's it for sure. Okay, that's all we need for that. 5. Good timing now. Good timing now. The functions f and g are twice differentiable. Okay, they show us one of them. The table shown gives the values of functions and their first derivatives selected. Let h be the function f of g of x. F of g of x. Find h prime of 7. Okay, easy enough. A little chain rule. A little chain rule. So, if a f of g of x, so that's if h of x equals that, then h prime of x is f prime of g of x times g of x. Just your standard chain rule. And then what we want to find is h prime of 7. We probably want to get this chart down here. So then we want to find h prime of 7. So that's going to be f prime of, what's g of 7? G of 7 is 0. So f prime of 0 times g prime of 7. Missed that there. What's g prime of 7? 8. What is f prime of 0? 3 halves. 3 halves times 8 is 12. Okay. Nothing more to say there unless y'all got questions. Next, B. Let k be a differentiable function such that k prime is f of x squared times g of x. Is the graph k concave up or concave down at the point x equals 4? Okay, fair enough. So f of x squared times g of x. So we'll go k prime of x is f of x squared times g of x. And then we got to find k double prime because they're talking about the concavity. So that's 2 times f of x times g of x, but then product rule. Also chain rule. Also chain rule. 2 times f of x times f prime of x. And then times g of x. And then plus g prime of x times f of x squared. Right? So we did the derivative of f of x squared is 2 f of x, f prime of x, times g of x. And then the derivative of g of x is g prime of x times the original. Yes, 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 sirree. Alright, now we gotta find k double prime of 7. No. 4. Because we want to know if it's concave up or concave down. So k double prime of 4 is 2 times f of 4 is 4 times f prime of 4 is 3 times g of 4 is negative 3 plus g prime of 4 is 2 times f of 4 is 4 squared, 16. Huh. So we got 8 times 9, negative 72, plus 32 is negative 40. So therefore it is less than 0, so concaving down. Okay. C. Let m be the function defined by that. Find m of 2. Show the work that leads to your answer. Okay. Let me copy this down. This is a fun problem. I like this one. So m of 2 is, let's see, 2 cubed is 8. 8 times 5 is 40. Plus the integral from 0 to 2 of f prime of t. Okay, so obviously that is the challenge. What is f of t? Oh, we don't know. Oh, but it's the... Oh, well, it's just f of t. The integral of f prime of t is f. So then that's plus f of 2 minus f of 0. Yeah? Yeah. So it's 40 plus 7, 47, minus 10, 37. Okay. Okay. D is the answer is the function m defined in part C increasing or decreasing or neither at x equals 2. Okay, so we just take the derivative of that. Take the derivative of m. What's the derivative of m? So m prime of x is 15x squared plus the derivative of an integral means it's going to be like this, right? I feel like I'm not entirely confident about that. 15x squared plus f prime of x minus f prime of 0, that was 10, right? Or was that f of 0? That was f of 0. That was 3 halves. So then what we're trying to find is m prime of 2, so we can see if it's positive or negative. That's what it was, right? It's the same spot, 2. Yeah. Okay. So that's a big number. That's 60. Oh, it's definitely increasing. It's increasing by a lot. What's f prime of 2? Unless that's massive. What's f prime of 2? Negative 8. That's not massive enough. Minus 8 minus 3 halves. That's definitely greater than 0. So it's increasing. Okay. That's what we wanted to do. I'm surprised it was so positive, but that's what we check our answers for at the end. We're looking really good on time, though. That's nice. Okay. Consider this curve. Show that. All right, we got a little differential equations up in this. So let's add a new page. And let's look 6a. So we've got 6xy equals 2 plus y cubed. And we want to find the differential equation of that to start off. Okay. So I'll just take implicit differentiation. So chain rule. So I'll do 2 or 6y plus 6x. I like to use m for slope when we talk about dy dx. So I'm going to do that. And then I'm going to say that that's 0 plus 3y squared times the derivative of y, which is the slope. Because that just makes it easier to now like solve for the slope. And so you see you're going to subtract that over, you're going to factor, and you're going to divide. So it should be 6y. I feel like I need to add another step in there to like actually show it. So let's go m 3y squared minus 6x 6y. So therefore it should be 6y over 3y squared minus 6x equals dy dx. Yeah. 2y. How did I not see that? How did I not see that? Okay, so then you factor out a 3, then you cancel that with a 2. So then it's 2y over y squared minus 2x. Okay, good. B, find the coordinates of a point on the curve at which the line tangent to the curve is horizontal. Or explain why no such point exists. So we got to set that equal to 0. So for B, we got to say, when does 2y over y squared minus 2x equal 0? Well, when y equals 0. So when y equals 0, what does x equal? Anything. Is that an asymptote at y equals 0 then? Or is that just like a horizontal line? Wish I could look at this graph. So it's got at y equals 0, it's got a horizontal tangent line. Well, no, then I should go to the top. Yeah, but x can be anything. No, x can't be anything when y equals 0. Oh, well, that's undefined. That point's not on the graph. So then you go up to this function and you say, okay, so 6x. Copy this down here. So then you go 6x times 0 equals 2 plus 0 cubed. You get 0 equals 2. So never. And that's the only time you get a horizontal tangent, right? And that's all they're looking for? Yeah. Therefore there'll never be a horizontal tangent. If there was, it would be at y equals 0. But the function is not defined when y equals 0. Yeah. Okay. C. Find the coordinates of a point on the curve where the line tangent is vertical. Okay, vertical. One way to be vertical is when the bottom is equal to 0. That we might have ideas for. So if we change colors, then we'll say when the bottom equals 0, that's y squared minus 2x equals 0. Now that's a parabola. Are we really about to solve a system of equations? I think we are. Okay, so here's what we want. So the deal is, this is when it will have a vertical tangent. But when is that on the graph? So the other equation, our actual equation, is this equation. So we want to know, when are both of those true? That means we have to do a system of equations, which is kind of wild. So I would actually do a substitution here and say something like y squared over 2 equals x. So what we have here is 6 times y squared over 2 times y equals 2 plus y cubed. Because look how then you have this is just 3, and then y squared times y is y cubed. So you have 3y cubed equals 2 plus y cubed. So then we have 2y cubed equals 2, y cubed equals 1, y equals 1. And then if y equals 1, we pop that up here and we say that if we do 6x times 1 equals 2 plus 1 cubed, we get 6x equals 3. So x is 1/2. So it should be at the point 1/2, comma 1. Because see, at 1/2, comma 1, the point's on the graph, right? So if x is 1/2, we get 3 on the left side. If y is 1, we get 3. But also, when x equals 1/2 and y equals 1, we get y minus 1 minus 1 for this, which gets us 0, which gets us 0 in the denominator of a fraction, which means the slope is undefined, which means it's a vertical tangent line. That's deep. That's tough, and it's not even part D yet. All right, see if we can do part D over yonder. Or maybe it'll take up too much room. But let's see. Part D. A particle moving along the curve at the instant when the particle is at 1/2 comma negative 2. Hang on. Is 1/2 negative 2 on the graph? 1/2 negative 2. So x is 1/2. That's 3. -2 is -6. And that's going to be -2. That is on the graph. So you can have multiple 1/2s. Multiple, okay. It's a little scary, but that should be fine. Oh no, that's fine. Okay. The position is increasing at dx dt is 2/3 per second. What is the value of dy dt? The rate of change of the vertical position at that instant. Okay. So its horizontal position is increasing. So at 1/2 -2. So I've got to get my x and y. So I got to go back to the top, 6xy plus 2y cubed. And I got to take the derivative with respect to t. So I'm going to go 6 dx dt y plus 6x dy dt. It's like what I did before, it's just I'm also doing it with the x's. The 2 still goes away. This is y squared dy dt. Because then the idea is, what all are we talking about? We're talking about a 1/2 -2, where dx dt is 2/3. We're talking about 1/2 -2, where dx over dt equals 2/3. And they're trying to get us to find dy dt. So we just got to plug everything in. So we've got 6 times 2/3 times y plus 6 times 1/2 times, I'm going to call it m again, like the thing we're looking for, equals 12 m. Okay. So then we cancel. That's a 2. That's 2 cubed. That's -8. Cancel. Plus 3m equals 12m. Subtract the 3. M is -8/9 is dy dt. And that's all I can tell you. So it's going down. Yeah, I'm pretty happy with my answers. Okay, I'm going to call that time. That's 41 minutes. That's pretty quick. I had an hour. It took me so long to do the first ones. I guess since I was warmed up, I was better. Hopefully I didn't get them all wrong. Now, it is time to check the answers. Before we check the answers, though, so I'm going to pause the recording to check the answers. Let's pull up Desmos real quick and check out what that graph looks like, because we can confirm everything there just by looking at the graph. So, I mean, it's really just a sideways polynomial, ain't it? It's like a sideways cubic polynomial. Oh, no. It's like a sideways rational function. Equals 2 plus y cubed. Yeah, it's a sideways rational function with a parabolic slant asymptote. Okay, so what do we find? 1/2 comma 1. That's right. No horizontal tangents. That's pretty clear. And I don't know how we can confirm that from the graph. But that's a pretty interesting graph, right? You're no more used to just seeing that like up and down. It's just you got a slant asymptote that's a parabola. Yeah. All right. Let's check our answers, and I'll see you back at the end. On the very first thing I messed up. As I remember kind of correcting this later on, this idea, but look how I said we were looking at when m equals 0, but we were looking at the point 0, 5, but this was our m value, and this was our t value. So I should have been doing, let's see if we can correct our answers and then get them right. And how much we actually have to correct. So this should have been 5, which means this should have been, instead of 10, I mean, that's just meaner. 35 over 4. And then, so when t is 2, it's 35 over 2 plus 2. Or plus 5. Which is 45 over 2. Is that what they got? Oh, yeah. How did he do so much more work after that? Yeah, 45 over 2. Okay. Oh, frick. I meant overestimate. I meant overestimate. I meant overestimate. Ah. I butchered it. Y'all know I meant overestimate, though, because we drew this line. And we were like, that's what we're estimating. This is the real thing. So the graph goes under. The real thing is under. That's what I was thinking about, was that the real thing was under. Tough. Alright. But then D, I got that right. I got the hardest part right. 40. I didn't write it the same way they did, but I got that part right. Alright, so that's that problem. Let me check number 4 now. Alright, so we beat him out on part C. He got part C wrong. We got part C correct. But part D, we just didn't really answer the question. Because they asked for the minimum value. Where even are we? They asked for the... Where even are we? They asked for the minimum value. Whereas we found the time where it's the minimum. So what we needed to do then was find the actual where it was at time equals 2. And so to do that, we would think about the same thing we hear of it starting, it's back at the beginning. Where does it start at, though? Oh, it satisfies that f of 2 equals 1. So we don't even have to calculate anything. Goes down until time equals 2. Yeah, so we had to say f of 2 equals 1. So that's the minimum value, because they even just told us that f of 2 was 1. Okay. So we got most of the points there. Now, L'Hopital's rule... I don't know, man. I think I did that good enough with the notation. Alright, let's go to number 5. Number 5 was easy peasy. Remember, I did say I liked that one. I just got them all right. Nice, quick, easy to check. All matching what he did. So let's go to number 6. So the only questionable thing was that I didn't put units on the negative 8 over 9, whereas this guy said it was units per second. But I really don't think that's necessary. So I think I did pretty good. I think I got full credit for number 6. I definitely got full credit for number 5. Well, L'Hopital's rule notation, maybe not actually. I don't know. Number 4. Oh, number 4 was L'Hopital's. No, 5 I just got full credit for. 4 was L'Hopital's. I was a little iffy on that one. 3 I just butchered. I made this simple mistake. I explained it all properly, but I made that little mistake. Here, I just plugged in the wrong thing. So that's really just like one thing that I did wrong. And then I wrote down that answer wrong from the calculator up here, even though I did all the math properly. So overall, I'd say pretty good result. Pretty good result. I'm pretty happy with that. I think it was a pretty easy test overall, I'd say. So, yeah, hope that was helpful for you. If you're taking it in 2024 or beyond, good luck.